Everyone, I'd like to introduce Kevin Logan. He is an engineering fellow at Magnite. Magnite is one of our gold sponsors for today, without which NIDC would not have been possible. So Kevin will be talking through the business case for using system-level languages for performance-critical applications, and most specifically, why Magnite chose Rust for those use cases. So take it away, Kevin.
Thank you. Yeah, so as mentioned, what I would like to talk about today is the kind of road Magnite and I went down together, coming from a lifelong C++ developer, myself, and ending in a policy change at Magnite for our low-level back-end systems language of choice end up becoming Rust. So to get started, I should probably start with some background. I've had this chat with quite a few people at the desk out in the hall, but what is Magnite? And the first thing you'll always hear is we're the world's largest independent SSP, as if that means anything to anybody outside of the industry. But that basically means that we're a supply-side provider, meaning we work with publishers, and we're the world's largest independent, meaning we're not the likes of Apple, Google, and Amazon. So we're not competing with the companies in some other industry. Magnite itself was formed through the union of Rubicon and Talaria, but has since acquired several other companies, including SpotX, which is one I came from, and SpringServe. We deal with hundreds of billions of daily impressions, and we hoard petabytes of data, and we have offices all around the world. But the largest office we actually have is our largest development office, I should say, is our Belfast branch. For myself, I'm an individual contributor. I've got 15 years of experience, mostly working on low latency programming. I'm a C++ enthusiast. I enjoy coding in my free time, and I spent far too much of my free time, mind you, reinventing the wheel. I've written operating systems, graphics libraries, stuff like that that has no real world use, but I just want to understand what's going on. I can be a bit idealistic about the intersection between performant code, readable code, elegant, scalable code. I always try to find that perfect intersection. Sorry, the screen went black. But yeah, I started my career near Denver, Colorado in 2009. I had about a 3-year stint in Viña del Mar, Chile, and I've been in Belfast since the very end of 2022. So I've talked about performance-critical applications in the sense of low-latency programming, but what is a performance-critical application? It's basically any application that has a costly performance constraint. A performance constraint itself can be broken into several different categories. Some I've listed here are CPU, GPU, memory, latency, bandwidth. CPU constraint, I think we're all familiar with, but the idea that you're just trying to calculate so much that you run out of time, or you end up having to scale up more and it costs you more money. All of these constraints work similarly. We're probably familiar with all of them. People who work in the cloud are probably very familiar with bandwidth cost implications. But the one I've focused on most throughout my career is latency. And so latency constraints are you want to do something quickly. I started my career in computer graphics. You want to have a high frame rate. You want to make sure you generate that frame in the lowest amount of time as possible. Now I'm in advertising, where we want to make sure we bid for an ad in the shortest amount of time possible while considering the most factors as possible. So when is something too costly, though? This is my personal opinion here, but if you're spending so much money on hardware or cloud bills or something else that you could fund an entire development team with that amount of money, you probably are well past the point where it would have been worth it. But these things should ideally be proactive. You should be considering performance throughout the design lifecycle of your software. But the way the competitive startup scene can be, and just competitive engineering scenes in general, a lot of the times we do have to put performance concerns on the back burner and say that would be harder, and we need to make a more pragmatic decision now. But it can end up coming back in the end and costing you a lot more. So let's say this is the Magnite story. Let's say we've identified a performance-critical application. So at Magnite, for example, we serve tens of millions of queries per second coming inbound. And so obviously anything we do there is going to have a dollar amount associated with it, the cost to serve that, even if we did almost nothing with that. 10 million per second is a lot. So in this influx of queries per second, we have different services that are all needed at different stages of request processing. Some of them can cost as low as $2 per billion queries, and some can cost as much as $500 per billion. So there's a huge range of things going on. Some of that's because it's 250 times more calculations, and other times it's because we've made poor choices in our design of our software, and other times we don't know, and we need to dig in deeper. So we're building this new service, and we have now deployed this service, and it's going to be taking 5 million of that 10 million QPS every day, all day. And so you read the title of this talk, you're probably thinking, we should use a low-level systems programming language for this, right? And you might even think, I think we should rewrite everything in Rust, which is not the case, and it's definitely not what I would vouch for or suggest to anybody. That's a good way to go bankrupt and get run out of business, but I think some people at Magnite still suspect that's what I'm actually trying to do, so we'll see. But what I would actually say is the problem with your software, the performance of your software, is always in the design of the software. It's not necessarily the languages or the frameworks you're using, it's the algorithms you're using, and it's always going to come down to that. The faster algorithm will always be faster in production. The lower cost algorithm will always be the lowest cost algorithm. You implement that algorithm in any language or any framework, it's going to be the same. The gotcha there, and why I can put that in bold and say always so hard, is because you have to really understand what your algorithms are doing. Just having an algorithm and saying, I looked at the code, you know, it's big O of n, see, it's linear, it only does everything once per the size of the data set. That's a very surface level approach at looking at an algorithm, but you really have to look at what your code is doing line by line, which you should know at some point in your career with the languages of choice, but you need to look at everything your code is doing and what it's doing, and that's a component of your algorithm. So I put this, it's turtles on top of turtles on top of turtles. Everything's an algorithm. Your line of code in Java that gets compiled or transcribed into Java bytecode that gets executed into machine code, that's all part of your algorithm. And if it's happening front-loaded through a just-in-time compiler, or when things are happening, if your objects are atomically reference counted and garbage collected for you, all of that is built in somehow to your algorithm. And understanding that will help you understand if you're writing the algorithm you intended to write. Okay, so based on that, you might think, I guess I don't need a systems level language, I'm off the hook. We're writing our game engine in Perl, everything will be fine, we just need to optimize, I guess. Well, that's where we kind of get into the weeds again. So if we're looking at the complexity of software that we write, we often talk about big O notation and how complicated an algorithm might be. And again, we can look at a piece of code. Here we have a piece of code that's quite simple. It's pseudocode I wrote, which means I wrote it in C++ and then I changed something to in, so it looks like pseudocode. But this is just code that's very simple to look at. It takes a list of something, iterates through it one time, finding all elements that are eligible, and then calls another function with that. So a very simple algorithm that you would probably see all the time. Hopefully you actually have something baked into your language that can do this for you. But for the sake of argument, say we have to actually implement this thing that is essentially filtering a data set and then passing it along. If we look at this pseudocode without knowing what language it's in, I can create all kinds of problems with the performance here by saying, well, if this is C++, or if this is Java, or if this is Rust, these things introduce different problems here. For example, first thing is we're creating another list, which we can assume is a linked list, but maybe it's a contiguous array, automatically growing contiguous array, maybe it's a linked list, we don't know, but those implications matter. If it's a linked list, it's probably going to have an allocation for every single time we do a push. If it's a contiguous array, well, if thing is too big, it's going to have to reallocate and copy every element every time it reallocates. And so we have all these extra copies happening over here, or we have memory allocations happening over here that we weren't actually introducing in our original analysis of the algorithm. If you look at this naively, it's just n. List has n things. We do n operations, and then we call something. We're done. That's n. But it's not. That eligible stuff push has between a log n and an n complexity. So that, in some languages, this is an n squared algorithm. And so you've actually written a terrible algorithm for your use case. In some languages. Other languages, a lot of the higher level languages, this will be a lot closer to an n algorithm, but it comes with a bigger n, because they're doing things like atomic reference counting. And if you're running on very large machines, Magnite tends to use very large machines for what it's worth. If you have 128 cores running this thing and they're doing a bunch of atomic reference counting unnecessarily, perhaps because of the way you wrote your algorithm, you're actually causing a bunch of cache clears and a bunch of cache misses, overall deteriorating the performance of your code because you wrote it this way. So there's a lot of hidden common problems you can have in your code that can hurt the performance if you just look at it at a surface level. So I've talked about allocations and copies and reference count. There's obviously also interpretation. A lot of languages are interpreted. There is undeniably a cost to that. Usually it's relatively low compared to the actual complexity of your application, but there is some cost to the interpretation that's part of your algorithm. Now, it should be mentioned here, interpretation often comes hand in hand with just-in-time compilation. Just-in-time compilation can actually be a huge boon to the performance of your application because it can just-in-time compile targeting specifically the machine you're running on, whereas compiled languages often have to compile down to machine code that would work on a large array of machines. So that matters a little bit less in systems programming where you're working on back-end servers, since you tend to know exactly the hardware you're targeting, but something to consider. So I'm kind of going back and forth here, and you might be wondering, what am I actually trying to say here? What languages should I use? Just tell me what I'm supposed to do then, Kevin. What's your take? But my take is basically that you should use whatever language or tool that makes your hardest problem easier. So you should identify first what problem it is you're having that's the hardest problem. Obviously, in the context of this talk, I'm talking about performance and latency. But in general, the software you're writing you should be writing it with tools that make that easier to achieve what you want to be doing. Sometimes your hardest problem is a deadline. They told me it needs to be done a week ago. Well, you probably shouldn't start writing Rust for the first time ever and try to deploy it in Rust without knowing what you're talking about. It's a bad idea. It's not going to work. Sometimes it's a lack of expertise. That's another thing that will be difficult for Rust, is there's not a whole lot of expertise in the ecosystem, and you need to make sure you can build something that you can then support and grow and expand, and you can make sure you have the infrastructure within your company to foster that. That's a time when Java is a great option. Java has a ton of experts. You can find Java experts anywhere around the world. There's a ton of them. And other times, it can be cost. And when it's cost, a systems level language might give you the control you need. So you generally need to understand for low-level applications, when you're trying to performance tune things, you're trying to control those things I was talking about, allocation, copies, et cetera. Those things are very hard to control. And they're hard to understand, and they're finicky, and if you write C code, you can control all of it, but you can also, shoot yourself in the foot a bunch of different ways. So you have to wonder, like, if I make the performance problem go away, am I going to make my new biggest problem scalability or the safety of your application or its flexibility? So you don't want to create a new, bigger problem. You're trying to get your biggest problem and make it easier. So when should you use these system-level languages like Rust? It's when they are going to make the problem easier for you to solve. But whatever you do, don't become the hammer that sees everything as a nail. There's a different language for everything, and understanding the limitations will help you get to good solutions. So given that, I'm going to go through an example, and we're going to start in Go. So Go is a language you're probably all familiar with. It's developed by Google since 2007. First release was in 2012. It's really, really good for writing synchronized code, high-level concurrent code. That's what it's all about. It's very easy to prototype, very easy to write something very quickly. It's generally considered somewhere on straddling that line between a low-level and a high-level, or like systems-level language or not, because it does have things like pointers and slices and understanding memory and whatnot, but it also has a memory manager, or a memory allocator, sorry, garbage collector. And there's a built-in runtime that's managing all of your Go routines for you. So it has some of the little bit of both sides, but it's trying to keep everything very simple overall. Some people say it looks a lot like C, and I don't disagree with them. It tries to keep things a little bit basic while taking away some of the footguns that C has. So let's look at an example of code, the exact same example from before. I just Goified it. So this is our application, or our algorithm that we're going to go through here, but it's written in Go. So we already kind of talked about what some of the hidden costs might be. So now that it's in Go, we can say what the hidden costs are definitely. So we're taking a slice of thing. A slice in Go is just going to be a pointer and a length. But then we're making another slice of a thing, and then we're copying elements over. And now we know we're definitely copying over here. When we call that append, eligible stuff thing, we're copying a thing object. And we've made no mention about what a thing is, so we don't know if that's a huge 1,000 byte, 10,000 byte, 10 megabyte copy, or if that's just a few bytes. But if it is a big object, that could be a huge concern that you're just copying a ton of data there. Also, we're doing a lot of reallocation. We start by making a new slice, our eligible stuff, and we start with a size of 0, and then we continue appending things. That's going to have an outsized performance cost the bigger the slice stuff is on the input. So we don't really know, but there's a huge potential for performance loss there. There's also some things that just aren't expressed well here. Like Can we change stuff? Can you look at this code and say whether or not we're allowed to change stuff? You can't know. Did they hand me stuff, or am I borrowing stuff? What am I doing? If I change it, am I going to break some kind of contract? There's nothing in the language semantically that allows us to express that. Neither Go doesn't have const or mutable, nor does it have the idea of ownership being passed around here. So we just have some stuff, and then we don't know if we can change it, and then in turn, we create eligible stuff, and we know we're not going to need it again. And so we pass it to something at the end, and we aren't able to express in any meaningful manner to something through the contract that it can then take something, or eligible stuff, sorry. There's no way for us to express that semantically in the language that we're done with eligible stuff, do what you will with it. So that's not great, but it's not bad. Sometimes you don't need to worry about that stuff. But obviously, in this context, we are talking about times when you do need to worry about that. So let's take this Go example a little bit further. Let's optimize it. These are just some simple optimizations. I made a few things pointers. So we're now copying pointers, which will always be the same size. We've reduced or eliminated the risk that the thing object could be 10 megabytes. So now we're just going to copy a pointer whenever we're doing the copies. We actually pre-allocated eligible stuff. We used a pretty common heuristic. We just allocated it to the size of stuff. It's a bit pessimistic. We don't imagine everything's eligible, but it's a memory CPU trade-off, and we decided we'll trade the memory to get the CPU time back. So we allocate one time at the beginning for a size that's guaranteed to be large enough. Now this application, or this algorithm only has one allocation instead of log n, and now it doesn't have nearly as many copies, or it does still have all the copies, but the copies are a fixed length of 8 bytes on a 64-bit system instead of being unbounded based on the size of thing. Before, if another developer came into a completely different part of the code base and changed the thing object, it could have destroyed your performance here if they added something expensive to copy. Now you're protected from that. You're just dealing with pointers, and the data is just going to copy the same either way. But again, we're going to talk about some of the concepts that Go's abstracted away from us. It's abstracted away that mutability we talked about before. We still don't know if we can modify stuff, and I keep bringing this up because that's the next stage to optimizing this thing. And ownership. We have these thing pointers, but we don't know who actually owns them. We know we don't own them, but maybe we own the ones that are ineligible stuff. Maybe we don't. We don't have a way to express that, and we don't know what we can do with these objects. But let's say we take an optimistic approach to everything, and we say, maybe we do own stuff, and we can change things. Then we can write the next level of the optimization for this function, which is going to be a partition in place. So generally, if you're removing items from a list, or adding items, or only retaining certain items in a list, a good way to do that, performance-wise, is to do a partition in place. At this point, we have reduced the allocations to none. Now it's not just one big allocation at the beginning. We're never allocating. Additionally, we're no longer copying more than we need to. We're only making a swap here. So this is Go syntax here for a swap. We're saying stuff of first bad, stuff of I equals stuff of I, stuff of first bad. So we're just swapping two items when we do that. And we're basically just keeping a single index that tracks where are the good things and where are the bad things in this array. So we can do this with a minimal number of copies, and now no allocations. And we're still operating on a pointer of thing, because we still don't want to be copying the data that may be large blocks of data. So this, again, it's a lot more optimized. This is basically, like, you could clean this up, obviously, but this is basically where you want to be performance-wise here. But is it the performance we want? And are we satisfied with this? Does this feel like the code got cleaner and better, or does it feel like it got worse and more dangerous? If you're on the side of thinking this code is harder to read and more dangerous, you're not entirely wrong. Like, this code now doesn't feel as good. It doesn't feel as idiomatic. Obviously, if it were idiomatic, you wouldn't even have a function for this, but that's not the point. You would use some external library for this. But we really can't express ourselves enough writing this algorithm to make ourselves feel good about it. But it works, and it's very well optimized. So now let's talk about REST. So you've all probably heard of REST. It was sponsored by Mozilla in 2009, and its first public release was in 2012 as well, but it was a 0.1 instead of a 1. It's a memory-safe, low-level systems language, but it gets its memory safety uniquely by not using a garbage collector, but rather using its famous borrow checker that just makes sure you don't do things that would be otherwise illegal, sometimes making you program with a hand behind your back. It does have a strong influence from functional programming. It was originally implemented in OCaml, and it generally strives to make undefined behavior or unsafe things and generally impossible unless you yourself use unsafe. the keyword unsafe, and then make poor choices. So I strive to never use unsafe. I think that's a general rule of thumb with Rust. So if we look at the Rust example, we're back to the original with this do something. What it would look like if that were implemented in Rust naively. Well, we're taking stuff as a slice of things, very similar to the Go version. We're making an eligible stuff. That's a vec, because now we need to very clearly say that there's a difference between owned arrays of things and unowned or borrowed arrays of things, whereas in Go they were the same type. Now we have a reference to a slice as our input, and we have a vec as the thing we're building that we own. But otherwise we just loop over stuff. Same thing, if they're eligible, we're pushing them into the vec, and then we're calling something. So there's only a few things that look different besides the syntax, obviously, than the Go version, and I would point out two of them. There's a call to this method called clone over here, and there's a reference over here happening on eligible stuff when we pass it to something. So Rust is actually forcing us to acknowledge that we're making a copy when we push the item into eligible stuff. It doesn't let us copy an item automatically. To copy an item, you have to call clone. If you passed it without calling clone, it would move the item. But that's where the Rust borrow checker will get mad at you and say, you can't move thing. You said you're borrowing it as the input parameter. So the caller still owns thing. You can't move that. So it just won't compile. So we need to say, fine, I'll clone it. And Rust is trying to tell us maybe there's a better way of doing this. But just to make it work and make it like the Go version, we clone it, and this all works. And its complexity and performance is very similar to the Go version. If we continue and get to our first level of optimizations, yep, we can do the same thing. We can allocate a vector with a capacity for all of the elements, just like we did before. And our vector is now, hard to see because it's kind of that grayed out color, but it's a vector of references to things. So those are essentially pointers again. So we're not going to copy the items there anymore. And you can see the call to .clone disappeared. And then I got rid of the reference on the call to something. So that means we are moving eligible stuff into something. We don't know what something's going to do with it, but if they want to take it, destroy it, sort it, do whatever they want, they can now. And we've done that without them needing a clone of it or a reference, because the reference will block them from mutating it. So same sort of optimizations here, but it feels more idiomatic than the previous version. We got rid of this unnecessary call to clone. We didn't need to add extra references where we didn't need them. Rust was actually trying to push us in this direction. This is the way it wanted us to write it in a way of thinking, and it helped us, pushed us in that direction. So now let's take it to the next stage and get that optimized version that uses a partition in place. So the algorithm is exactly the same as the other one. You'll notice we're now taking stuff as a mutable item, and we're now taking it by value. We're no longer taking a reference. We're now saying, I want this thing because I'm going to change it. I'm going to do whatever I want to it. If you don't want me to do whatever you want to it, you can pass it and say clone. So if you want to give me my own copy, you can. I don't decide what you do. So I'm telling you I want to mess with it, and I'm going to mess with it. So that's expressed in the language grammar. And then we do the same algorithm as before. There's really no differences here. At the end, we call this stuff.truncate. So we're just truncating the size of our vector. It still maintains the same capacity, but we're changing the length to the number of items that matched. And we've effectively partitioned away every element that isn't eligible. And then we call something, and we're passing it along again by value, which is moving the item to them. So we're getting a vector moved in. We're sorting it, basically, but a partition is faster than a sort. So we're partitioning it, and then we're passing that partition down, and they can go on and do something similar. And we don't care, because we know it's all safe, because it's all expressed through language grammar. I'm not asking here, did I move stuff into something? I absolutely did. It wouldn't compile if I didn't. And I'm not asking if they gave me a copy or they moved it into my call. They absolutely had to. This is mine now. And it's all enforced by the compiler. So I can't make a mistake by using it or changing an object they didn't intend for me to change because they had to have given it to me in that form. So again, Rust made it easier to write this code in a way that you can reason about and be like, this is safe. I don't need to worry about writing a comment at the top of this, say, please don't expect this data to never change, or worry that some developer is going to come on later on and change that assumption or do something. It's all expressed in the language grammar, and you just can't make that mistake. So that's the really thing I want to point out here. It's easier. It made it easier for me to write this harder, optimized version of the code. So it was the right tool for this random do something example. But what did it do in the real world? The impact of Rust at Magnite was pretty huge. So we have a self-inflicted difficulty at Magnite, and that is basically we use very large machines. They tend to have between 128 and 256 cores. And most languages and frameworks don't scale up very well. They can't use all of that. So multiprocessing helped a lot. We originally wrote an application in Go, and we had to try to multiprocessing it. We can get more throughput by multiprocessing, get more usage of the CPU, but we couldn't get all of the CPU used. But writing it in Rust, it just worked. Like, it just scales up because we were able to apply asynchronous programming techniques how we wanted to, because the language gave us the control, the safety, and the assurances that we were writing code that made sense and let us control those things. The upfront cost difference between the Go version and the Rust version of the server that took, or the service that took 5 million QPS was $1.2 million in services, or in upfront server costs. It then enabled us to write a highly optimized radix tree implementation specific for our use case that we wrote in Java, Rust, and Go, and all of them felt a little bit icky, except the Rust one, which is very easy to, again, verify that it is verifiably safe. So that heavily optimized radix tree brought us another huge win and saved us another $2 million in upfront server costs. We went from a 2,000 requests per core per second to 20,000 with both of those changes. And a projected amortized savings of $1 million a year. And that spawned a conversation that resulted in Rust being elevated to a level within Magnite where we want to use it for all low-level performance-critical applications going forward, whereas previously there was a lot of discussion about narrowing the scope of languages we would use at Magnite rather than broadening it. So that all said, the final points I'd like to make are just use the right tool. I hope your takeaway from this isn't that you should write everything in Rust. Rust might solve a small subset of problems, but it might solve them really, really well. And be an expert, don't be a hammer. Know where your limitations are, know where the limitations of the tools you use are, and just focus on the problem you're trying to solve. And solve that, and try to find the best way to solve it. I also say, I have to say it, performance matters. There's a lot of people in the industry in general who will not think that performance matters. It does matter. It always matters. It just might matter infinitesimally small amount. But a lot of companies get themselves in that trouble where they write not very performant code to scale up, and then once you have scaled up, you have a lot of tech debt on your hands, and it can be very difficult. And it's not really that much harder to write performant code, but it is harder. So I understand how we get there. But where we can, we should take the time to write code in a good way where performance is a consideration from the ground up. The other thing I'd say is Rust isn't hard. It's hard if you do the wrong things with it. It's hard if you want to mutably borrow a value 2 different times, because you can't. But it's not hard. It's forcing you to consider a few things that you should be considering anyway as a low-level engineer. Coming from C++ myself, you already had to think about lifetimes. You already had to think about data races. You had to think about those things. Now the compiler's making you think about them. And it's not so that you don't have to. You keep thinking about those things and you line up with the compiler. But yeah, every time, now and then you make a mistake and the compiler catches you in your mistake and tells you. Other times you don't make a mistake and the compiler is a little too conservative. And that's okay. That's a good trade-off in my opinion. But finally, have fun with it. You're supposed to be having like the most fun you can. You're obviously working most of the time, but try to do something that keeps you engaged, keeps your teams engaged, keeps people motivated. That's where you're going to get the best software out of people. That's where you're going to get people writing the best code. Just don't become that focused on one thing kind of person. Expand your horizons, find out what else you think is fun. I say that as a 15-year C++ developer that ended up having a lot of fun writing Go, and in turn a lot of fun writing Rust. I didn't expect that. I thought C++ was the only one for me. Expand your horizons, there's a lot more out there. With that, that's it. That's all I got. Thank you.
Thanks so much, Kevin. That was fantastic. I think we have enough for one small question. Oh, here we go.
Thank you. What was the learning curve, right? Like going from a C++ developer to becoming proficient enough in Rust to get all these savings that you have demonstrated in Magnite?
Yeah, I'd say it went pretty smoothly. Like I said, I think a lot of these things that Rust makes you think about are already things you need to be thinking up as a C++ developer. I can't say that that's consistent across organizations writing C++. Some of them don't have a very high bar of sanity in the code, so to speak. But you can write C++ like it's C with vectors, and then you're going to have a long way to go before you get to like saying Rust would be an easy transition. But if you're using modern C++ with RAII and trying to avoid using data structures that are unsound, and for example, C++ 23 coming with the monadic optional, trying to enforce using things in a way that is inherently safe, if you're already thinking that way, and C++ in general going in that direction, it just always keeps all the baggage of all the bad ways of doing things. If you're keeping up with C++, you're keeping up with the ideas that ultimately gave the birth to Rust. So it shouldn't be that bad, and I didn't find it that bad. I am somewhat, like I said, of an enthusiast, so I will bang this stuff out for fun in my free time, but I found it fun and not so bad. Thank you.
Brilliant. All right, give it up for Kevin.